All right, so here we come to the session 3, which is also the last session for today on the heat transfer, and we goes into the work example. So example 7, this is hold on, let me just try my pen. Why? Why every time I just try with my pen and then okay, it's done. Okay, example 7.1. Let's start again. So this is plates, elements, and then we are going to find, calculate the heat transfer inside these plate elements. Okay, demonstrate the heat transfer by solving the problems as shown in figure 7.1. So this is a plate. Okay, this is a plate. I don't know, it's a steel plate or this is a metal plate, aluminum plate, I don't know. So there will be the plate itself, okay, it will have a heat, okay, generate heat as in the informations as over here. And then the thickness, okay, this is the width of the plate is 0.4, the height of the plate is 0.2, and then there is a thickness. Okay, usually we assume that we take a surface. Okay, we take a surface. But if the thing comes with a thickness, okay, with a thickness, then the information here, the Q, okay, have to times the thickness, and then the K also have to times the thickness. Okay, just we need to do some conversions in the units and in the values. Okay, if some of the case that the thickness is not given to you, and then this will be in Q, let's say equals to 50 W over M square, then we no need to times the thickness. Okay, perhaps this is also not given to you in such a huge number, then we can omit the impact from the thickness. But in this case, we had to take care of the thickness. Okay, and we have the flux. We have the flux of the what do you call heat transfer inside the plates. Okay, here is given to us is equal to 0, and here is also equal to 0. That means this is a known. Okay, oh yeah, the T, the heat transfer is already known. Okay, so this is a Dirichlet boundary. Okay, here is also a Dirichlet boundary. This is also a Dirichlet boundary. Okay, and here the T is unknown, but it gives to us the flux, so we can do the calculation from this point onwards. Okay, so for step-by-step demonstration, so only 4 nodes assembly is going to show to you, and then later on we will go for the 8 nodes. Then, but here we just emphasizing on the 2 elements because the calculation will be very complicated. Okay, for 8 nodes, and then we can compare the results with the software calculations. Okay, after that we use a denser number of elements and then compare to the software calculations. So how do we do it? So this is the element that we have. Now we put the elements into 4 times 4 elements. Sorry, shouldn't say 4 times 4. We change it into the 2 times 2 elements. Okay, so we named our element 1, 2, 3, and 4 over here, and then we name the degree of freedom. So from 1, 2, 3, 4, 5, 6, 7, 8, 9 over here. So this arrangement is similar to what we learned in this morning on the assembly of elements. So later on, we always refer back, okay, to what we learned in this morning to form the global matrix. Okay, for the local matrix we have, okay, for each of the member we have it, and then how do we form into the global matrix? Okay, so look at the global matrix. Okay, so this is the local matrix that we have here. So this is the equations that you can get from the list or from the exam reference, and then from inside these equations we know our kx. Okay, we know our ky. We know our A. We know our B. Okay, any more things? Any else? No, no more things. Okay, so basically all the parameter inside this equation is solvable. Okay, we know the value, so we do the calculation. For example, for the one, kxb over 3a divided by kya times the 3 divided by 3b. So you are going to get this value. Okay, so you continue to do the calculation for this second one. You're going to get these values over here and so on. So for all the things that we can do the calculation, and this is the K matrix. Okay, the matrix for the element number one for this. Okay, secondly, we look at our division. Okay, divisions of the elements. So we notice that the division is same. The width are the same, and then the height are the same. Okay, the sizing is all the same. That's why when we develop the K1, okay, because we have the A, we have the B, we have the KX, KY is all in the same, so it will be equals to the K2. The stiffness for number 2, it will be same for the stiffness number 3 and number 4. Okay, so this thing, I can use it for all the equations. Okay, now if your division is different, okay, something like that. This is 1, this is 2, this is 3, and this is 4. Okay, then it will be not equal. Okay, it won't be equal. Then you have to do the calculations for the matrix one by one. Okay, so this is the things that we have to consider when we do our analysis. So it's always okay to simplify the problem, or just to start, you always make as simple as possible. Then the process can be repetitive. All right, so from there, then I come up with the internal heat generation. So it will be equals to this. Okay, the heat transfer is also the same. Okay, the heat transfer is also the same. This is the flux. The Q. Okay, that we tried to solve earlier. So here the Q will be equals to the Q divided by 4. And remember the Q, you have to times the thickness of 0.1. Okay, so from there, I got my internal heat generation is equals to 0.025. Let me just check whether the calculation is correct. So we have the 50 times 0.15 divided by 4, 1.25. Oh, yeah. You have to follow the equations over here. You follow the calculations over here and to get the equations over here. All right, so this is for the internal heat generations. Okay, now we try to assembly the elements in the global scenario situations. So this I get from the assembly from the previous load, okay, from the previous example, because we are following the same derivations. Okay, we have the same width, and then we divide it into 4 elements, and all these are the same length and the same height. So I can use the same assembly of elements from the previous work examples. Okay, when you have it, then you have to identify what are the metrics to put in. For example, here is K11, so you have to put the K11 into here. Okay, here is a K12, so the K12 in here, you have to put in there. And this is K22. Okay, K22 is over here, plus K11 plus this thing, okay, to put inside here. So 33 plus 33 equal to 66.66. All right. this is the same, K11, 33.33, and this is 6.66. So 33.33, 6.66. So this is how we move the things into here. Okay, so you have to fill it up one by one. This is a 9 times 9 matrix, and yeah, this 0 should be moving here. And then this 0 is actually under here. Okay, so sometimes you just miss it. This over here, this is over here. Okay, and when we look at the R over here, so the R is equal to 0.025. Now this is 1 plus 2, so it becomes 0.05. Okay, the largest one is here when we have a 4 corner that is going to contribute, so it will be 0.025 times 4 equals to 0.1. All right, so that is the global equilibrium of equations, and from the calculations we know that these are the metrics, and then this is also the transpose of the values, and our degree of freedom is over here. Okay, for the whole calculations over here, if you want to use computer software like Excel spreadsheet, then you can generate the result very fast. Okay, but if you're using hand calculation, this is a 9 times 9 times 9 matrix, so it is still very huge. Although the value is here, but it's still very huge matrix, so mistakes could happen along the way. So we have to try to find the boundary conditions and try to simplify the problems. Okay, so from the questions, we know that this location is a dirichlet, and this is also the dirichlet. So when we divide the panels and try to name it, this is 1, 2, 3, and then I think this is a 4, 5, 6, 7, 8, 9. Okay, so from the drawing, or from the information given to us about the drawing, then we know that for this the t is equals to 0. Okay, t equals to 0, t equals to 0. So this one, this one, this one, this, and this. 1, 4, 7, 8, 9. Okay, so we have the 1, 4, 7, 8, and 9 is equal to 0. So number 1, I can cancel it out. Number 4, okay, number 7, number 8, and number 9. Okay, that is a cancelling out. And if I go to the matrix, so number 1, this is moving. Okay, number 4, number 7, this number 8, and number 9 is also moving. Okay, it's also moving to the side. So what I left over here will be these 4. Okay, these 4, this 4, and another 4 over here. So it will become a 4. Sorry, I think it's changed to the pen. It will become a 4 times 4 matrix. Okay, we have the 4 times 4 matrix over here. So this is actually number 2, number 3, 2, number 3, number 5, number 6. Okay, now if you are solving using the computer software, you found out you can solve it very fast. But hand calculation, okay, this is very difficult. Okay, and very easy to make a mistake inside there. Now the whole thing, because of the boundary conditions, become here. Now it will be much more easier to use hand calculation to do the calculations. Okay, so what we need to do is we just either you can form the equations and then solve simultaneous equation to find it, or we can transpose this over here. Remember to do a transpose. Okay, then we just solve the answer, we just solve the equations, and we will get the answers. Okay, the question is asking us to find what is the flux, okay, degree of freedom for the boundary conditions that is inside the Newman boundary conditions. So this is the answer that we can find. Okay, so this is based on the 2 times 2 matrix. 2 times 2 matrix. Okay, if I divide, okay, my member to become a much more complex, this is 4 times 4, maybe I do an 8 times 8. Okay, I just divided my member becomes smaller size, so the result will be different. Okay, the result will be different. So here is the results. Okay, but this is using a computer software to do. So this is the 8 times 8. Okay, and this is the FEM software. I think it's a LUSAS or something like that. FEM software, or this is a MATLAB. Okay, to get it, so you can see that the distributions, okay, or how should I say, the fineness of the data, okay, you can compare the fineness of the data will be different over here, okay, when you come into here. So it become very, very fine, and then the distribution is much more, okay, it's much more realistic. Okay, this one is like too much digital. Like now you're taking your photos with your handphone, and then if you put a very low pixels, okay, you will get these results. Okay, but you increase the pixels or using the new handphone, which have a 4K and 8K, perhaps these are the results that you receive. Okay, so normal human, we will love, okay, we are going to love these results. Even for photos and so on, you want to be a very fine results. But this also means, okay, increase of the definitions, okay, increase of the processing types, and so on. So it's actually very increase the usage of your power inside your computer. So this is the pro and also con on the results that we are obtaining. Okay, so we just put the result into a table. This is the calculations using the manual calculations. Now I use a software and increase the node into 8 times 8. So I got the values over here. Okay, it's similar but different. Okay, it's slightly similar but eventually it is different because of the fineness of the model that you try to analyze. Okay, if you increase the software, this could be like 100 times 100 elements, I don't know. But you found that the results, okay, for a very fine result is also similar to your 8 times 8. Okay, it's kind of similar to your 8 times 8 formula. So what we can say is that when we do 2 times 2, our result may be not very good. Then we increase maybe 4 times 4, the result increase a little bit. Becomes 8 times 8, the result repeat it. Then maybe from 8.8, we go for 10 times 10, we go to 20 times 20, up to 100 times 100. The result are almost the same. Okay, this is 2, 2, 4, 4. Over here is 8, 8. Okay, and then you have a 10, and then you have 20, and so on. So the result is quite stagnant or statics already. Okay, that means the 8 times 8. Okay, this is our optimum model. Okay, and this study is called a convergence study. Okay, because we just assume we divide the material into 2 times 2, I mean 4 elements inside there. So we don't know how sure the value is accurate to the actual one. So we just divide into final model, but the calculation will become double or times 4, and then become final and final again. So from this study, it's shown that from 8 times 8 onwards, the results are quite steady. They are quite the same. All right, so you no need to go for very refined. You can no need to go for 100,000 times 100,000 over here. It will takes very long time for the computer to do the analysis, and then very easy for you to key in some wrong parameters, and the result go haywire. Even everything's are correct. Okay, the time you spend is manageable, but your results for 100,000 is actually the same as the result for x times x elements. Okay, so we do the convergence study. From there, we got what is the optimum meshing for our models. Okay, any questions up to here? Okay, if no, I try to show you through the I try to show you through the Excel spreadsheet on how do we calculate the values over here. All right, I just stop my slides for a while. If you have questions and you don't want to interrupt me, you can always type your questions in the chat box. Okay, when I have a break or what, I can always read and then try to answer you. Okay, maybe I do make it larger. Okay, so this is the heat transfer examples when I get from the examples 7.1. Okay, so I hope you can see my Excel spreadsheet and what I'm doing the changes in the spreadsheet. Okay, so I put in the parameters. So originally the width is 4, the height is 0.2, is all calculated in meter. The kx and ky, originally this is 400, 400 W over mk. So I times the t times the small letter t, okay, equals to 0.1. So I got this value. Okay, similarly, this one is actually 50. The unit is Wm over 3. Now I times the t equals to 0.1. I got is equals to 5. Okay, so that is the things. Now the shape is like that. This is a 0.4. This is 0.2. When I divide it into 4 elements, so here will be 0.2 and here will be 0.1. Okay, so this is the A values and the B values that I keyed into the Excel spreadsheets. Okay, so I need to solve the K matrix. The good thing is in this scenario, because the symmetrical and balanced derivations, once I solve K1, it's the same for K2, K3, and K4. Okay, but if I draw different things, if I draw something like this, okay, then it won't be equals. You have to solve one by one. Okay, for the matrix. Now it is the equal, so we don't need to worry about that. And yeah, so each formula involve the k, x, k, y, a, and b. So I do the calculations. I just put it inside here. Okay, so if you can see my calculation lines, so this is how I key in the calculation in here. Sorry, into the matrix. So if eventually, if I just change the values over here, let's say 50 and 50, you can see that the value is changing. Okay, so this is the good things about Excel spreadsheet. We develop a good spreadsheet for a particular case that you can change the parameter and get different answers. All right, so I do the calculation. So this is for the K11, and then this is for the K12. Okay, and then K13 and K14. You notice that I put the equal. Okay, it's because I do the calculations over here. Okay, the calculation is on the columns, and this is just a transpose. Okay, so it is the same but transpose. So I just transpose over here. Okay, transpose over here, transpose over here, transpose over here. Okay, similarly, if you have here, then it is transposed over here. All right, so these are the things that you can able to do, and then this is where I form my K matrix. Okay, and the calculations for the Q for the Higgs generations. So it is also all is divided equally. So what I need to do is B7, which is over here the Q, okay, times the A, okay, QA and BQAB divided by 4. Okay, Q times A times B divided by 4. So I got my values over here. Okay, I do the calculation for another two values. So the good thing is, I did it for the element 1, I can continue to do the same. Just pick up, don't need to do it again. Just pick up the value for the element number 2, 3, and 4. Okay, now I have to do the assembly of elements. Okay, so this is the original equations. And for each matrix, so these are the numbering of each matrix that I have. So that I have to put it inside here. So this is a K11, K12. So here, I just take the K11 from here. It's equals to B12. Okay, B12. When I go to K12, it's equals to C12. So C12 is equals to this value. Okay, and then it goes to K21. So it's equals to B13. So B13 is over here, 13, yeah, this one. All right, take note on this, this one. Okay, so it is summations of the two value, 22 plus 11. So when I comes to the equations over here, okay, it's the same, B12. Okay, B12 for K11, and then B12 for K12. Okay, K11 and K22, sorry, K22. So it is the same, so I can get the values over here. Okay, so in Excel spreadsheet, then you have to key in all this formula in the matrix one by one. Okay, easiest will be the 0. If there is a 0, then you just key in a 0. There is not much different with that. But each other formula, okay, you have to key in the matrix, and this matrix is actually referred to here, which we have already do the calculations at the early time. Okay, so we have the matrix, we have all the DOF, the degree of freedoms over here, and this is the heat transfer. Okay, sorry, heat generations inside the things. So I put the values inside the calculations. This is what I got. Okay, the green color is the matrix. Okay, the blue color, this is the degree of freedom, and this is what I got. Okay, for the R. So 0.25, this is plus 2, and then this is 4 equations. Sorry, this is the 4 equation that's add together. Okay, now when I form the equations, the next step is to know our Dirichlet boundary. Okay, so in this case, the Dirichlet boundary is the left and the top is Dirichlet boundary. So from that equation, from that onwards, I can know that my T1, T4, T7, T8, and T9 are equals to 0. Okay, so I cannot cancel it inside the Excel. So what I did is I just highlight. So this is the one I cancel, T1, 2, 3, this is number 4. Okay, 5, 6, this is number 7, 8, and 9. So these are the metrics that I'm going to cancel. Okay, and this number 1, number 4, number 7, 8, 9 are the metrics that I move to the right hand side. Okay, I can move to the right hand side. So I just highlight in the dark gray to eliminate, to show that those number is being eliminated, and then leave all these values, and I put it back into the matrix form. Okay, so you can notice that this 4 value is actually the same as this one. This 4 value is the same as this one. All right, and this is my unknown. I left only T2, T3, T5, T6, only 4 unknowns. And then this is the value where I get from here. Okay, 0.05, 0.03, 0.1, 0.5. So this is the remainders of the matrix for me to solve. Now inside the Excel, that is a good way to how to solve the matrix like this. Okay, so what I do, I can show you the calculation is over here. Okay, so it's a matrix multiply. So MULT, matrix multiply, and then I have to throw this thing. Okay, I have to move from the left to the right. So when it is moving from the left to the right, so I have to do the matrix inverse. Okay, matrix inverse from B76 to E79. So B76, E79 is as highlighted, is over here. Okay, and this value multiply with what? Multiply with this equation, with this number. Okay, so this is the, what do you call this? This is a G76. So G76, okay, up to the bottom here is G79. Okay, so up to G79. So this is a matrix inversions and also a matrix multiplication command from the Excel. Okay, so you finish the commands, you key in the value, is all these values are correct. Okay, all these values are correct, then you're going to get this answer, which is similar to what is published inside the book. All right, so this is an illustration by using the Excel spreadsheets. Now, the good thing of Excel spreadsheet is, okay, once you know your Excel spreadsheet is correct, okay, this is correct, then you can actually change the parameter inside here. For example, I can change different A, different B. I can change different heat generation, change the the heat transfer coefficient. Okay, change the width, change the height, thickness, and so on. Okay, at the same time, I also can change my Dirichlet boundary. This is following the book, okay, where is the 0, and I can change, like I only have the Dirichlet boundary at the bottom. Okay, I only have the Dirichlet boundary at the bottom. So this is T1, T2, and T3. Okay, so I can cancel out T1 to T3 over here, cancel it out, and then this thing, I can move, okay, to the right hand side of the corner. Then the rest have to do the calculation. This, what left over will be 1, 2, 3, 4, 5. 1, 2, 3, 4, a 6 times 6 matrix. Okay, what I left over will be a 6 times 6 matrix, as it shows over here. So this is my 6 times 6 matrix. Okay, and then my unknown, we also have 6 unknowns over here. Then I just move the things and then into the M inverse, if I'm not mistaken. Okay, using the M inverse and M multiplications, I got my results. Okay, you look at the result is actually different than the result, sorry, here. The results over here is different than the result we got previously. Okay, because with the same objects, with the same heat transfer, what do you call the procedure, but because the boundary conditions are different. That's why the answers that we get is also different. All right, so this is examples of solving the questions by using an Excel spreadsheet. Okay, you have the choice. If you are like me, you prefer to use the Excel spreadsheet so you can repeat what I'm doing, okay, for a heat transfer of rectangular projects. However, if you still prefer the way as taught by Dr. Razin using the Octave, by all means, you can use the Octave. Okay, in the end, this software is going to help you to solve the problem when you have a different, we call it case study or different parametric study. We change the boundary, so the result will change. Okay, we change the geometry, the result will also change, and the changes will be easy to check and easy to calculate because all will be done by the Excel spreadsheet. Okay, any questions up to here? Okay, maybe I have to switch a few software, then I just share my screen. Okay, so this is the Excel that you see. And if I change to my example 7.1, you can do the comparisons. Okay, so this is from the book. Okay, the answer from the book. If you develop your Excel spreadsheet, you put in all these consideration and the equations that you key in from here to here is correct, then you can get all this. Okay, the matrix is same as what we have in the book. Okay, same as what you have inside the book. And here, this is the procedures to simplify the matrix. So this is the end of the matrix that we simplified. You can compare to here. Okay, this is the matrix that we got, but I put it inside here. So you can compare the two matrices. So the value are the same, then the Excel spreadsheet is correct. Okay, and this is the value that I got from the before that. So it's the value. So in the end, I do the calculations T2, T3, T4, and T5. 2, 3, 4, 5. So this is the answer. I compare my answer to the answer in the book, so they are the same. Okay, which means my Excel spreadsheet is okay. Okay, so this is the way of using Excel spreadsheet to do the calculations. And you can see that for 4 nodes, when we increase the number of elements, 2 times 2 to 8 times 8, and so on, so the precision or the accuracy of the value will also be improved. Okay, now I goes to the same example, but now I use 8 node elements and only 2 elements are considered. Okay, because you consider too many elements, then the calculation will be too huge. Okay, I just divided this is into 1 and this is into 2. Okay, only 2 elements. So the arrangement of the node is shows over here. Okay, T1, T2, T3, T4, T5, go up to T6, 7, 8, got 9, 10, 11, 12, 13. Okay, and still remember, this is the matrix for 8 times 8 nodes. It's a very huge. So just now, ask where is the values over here. Eventually, it is or appears in these parts. Okay, just mix up inside the applications. Okay, so what you need to do is you have to base on these equations. Okay, based on your kx, ky, a, b, and then you do the calculations. You got the results over here. Okay, you repeat it for the second one, the third one, the fourth, and so on until you finish the calculations. The good thing is over here, this is actually a transpose. Okay, it's similar to here. So this is kind of shortcut that you can do. Of course, you can do the calculation as well, but this is actually the same. Okay, for the matrix arrangement, this is actually the same. Okay, then you form your matrix. So my left matrix and my right matrix are the same size. Okay, so this line and this line and this line are the same. This line and this line, they are the same. Okay, so when I finish one calculation matrix, I can do the same for the second matrix. Okay, this is the internal heat generations. Okay, inside a quadratic member, I do the calculations. So these are the heat generations inside the quadratic member, and 8 nodes. Okay, for one element. For one element, you will have you have oh, I think I skipped some of pages. Okay, never mind. We just follow the things. So it is 8 elements. We have how many? We have where is the 13. Okay, we have 13 equations to solve. But because of the boundary conditions, we can simplify. Okay, T1 over here. All right, T2, T3, T4, T5. T6 is over here. Okay, T7, T8. Okay, sorry, T T6. Too high. Sorry, I just need to change it a little bit because I have a T6, T7, T8, T9 is over here. Okay, and then we have a T10. Okay, we have the T11, T12, oops, and T13. Okay, this is T10. So all these are the boundary in the dirichlet, so we know that these are equals to 0. Okay, from the calculations, we can simplify the matrix into a much more simpler format and then arrange like this, and we do the calculations, we are going to get, okay, we are going to get the answer of the heat transfer as shown over here. Okay, I just compare my 8 nodes element. This is only 2 elements, having 2 elements, but the result is already, okay, very close to the software. Okay, so this is the advantages of when you're using a quadratic element, an 8 nodes element instead of a linear element. Okay, even though the calculation steps are the element is not very much, okay, but because of the nonlinearity or the quadratic functions, then the results you got is actually much closer to the accurate one. Okay, so the 8 nodes elements, okay, compared to the software, they are much more closer. It's even better, okay, even better than the 4 elements in the linear status. Okay, this is the result of the 4 node elements. 4 nodes element in the 2 times 2 metric elements. So again, the result is quite huge difference. Okay, compared to 8 times 8 and the software. So this result is actually quite close to the 8 times 8, even though you have only 2 times 1 matrix inside there. All right, so that is the illustrations. Okay, but for the 8 nodes element, not much calculations I have made. I haven't developed the Excel spreadsheet for this 8 times 8 element yet. Okay, so I don't have the Excel to show you, but the calculation will be the same as when we do it for the 4 times 4. Just the matrix will become huge. And then in Excel, you can then do by steps, okay, line by line, like inside the octave, you have to key in the equations one by one inside different cells. Okay, so this is the results and compare the results. This is 8 times 8 linear. Okay, this is I don't know, 100 times 100 or maybe 1000 times 1000. Okay, but the result is actually quite close. Okay, the result will be quite close with these 8 nodes, 2 elements, 1 and 2. All right, so that is basically the illustrations of the heat transfer inside a rectangular plate, a simple one. And then how do we use the manual calculation to show 4 nodes elements? And we go very fast on the Excel spreadsheet. Okay, last but not least, we solve the same problem by using 2 elements of 8 times 8 node elements. Okay, so this is summary of lessons that we learned today. So you can check yourself. You still remember what is a continuum mechanics and how does it relate to our lectures for today? Okay, and then you know what is a scalar and the vector elements. Okay, when do you deal with scalar? When do you deal with scalar and vector elements? Then we learn about the boundaries. We have the Newman boundaries. We have the Dirichlet boundaries. Okay, now steady heat transfer plus solid. Okay, we know the theoretical derivations of the equations. All right, and then from these theory equations, we convert it into the finite elements model derivations. Okay, so just in the intermediate, we do the element assembly. How do you change from local? Okay, that contribute to the global. All right, and then we do the example 7.1. Okay, we have 1, 2 times 2, 4 node elements, and then 2 times 1, 8 nodes element examples, and then we have the Excel elaborations. Okay, the source code. The source code to do the example is presented inside the lecture notes. So you go to the behind of the lecture notes, you identify there are pages of that is for MATLAB. Okay, for the MATLAB of the source code, but you can copy the source code and paste inside the Octave, and then hopefully from there you can get the same results. I think I come to the end of my lesson. I thought I would be ended in 3 p.m., but it seems that we ended early. For any questions up to here?